In this video, we will be defining the definite integral. Now, in our previous videos, we looked at the idea of left and right Riemann sums, and we sort of built our way up. Our introductory exploration, we were computing total distance traveled, and we found that was equivalent to computing the area between the graph of the velocity curve and the x-axis over time, over the time interval which constituted the trip. And we saw that we could approximate that with left and right Riemann sums, which are sums of areas of rectangles. We also seen that to get closer and closer to the exact area, in this case the exact distance traveled, we needed to take more and more rectangles of smaller and smaller widths. This indicates that we need to find a limit. So the exact area could be found by taking a limit of either the left or the right Riemann sums as n, the number of rectangles, approached infinity. And consequently, delta x, the widths of the rectangles, approach 0. So for the classes in calculus that I teach, like Survey of Calculus and Calculus 1, those introductory classes, we will use the following as the definition of the definite integral, which gives this exact area as the limit of right Riemann sums as n approaches infinity. So in the notation below, we will see that the delta x in the right Riemann sum has been replaced by dx, and this part should be kind of familiar to us because remember when we did derivatives we said the limit as delta x approaches 0 of delta y over delta x became dy over dx. So in fact the dx in the notation below, and let me just kind of flip down to the notation, so the dx right here in the notation really can be thought of as just notational only. So that dx basically just indicates that x is our variable, and it's really kind of there for notational purposes. But it's also nice to think of it a little bit as to what happens to this delta x here when we take the limit. It becomes this dx. So delta x is a change in x. We can think of this dx as sort of like an infinitely small change in x. That's not really precise, okay? So that's not really technically a correct statement, but it is, sometimes it's a useful way to think of it. So, so notice that delta x was b minus a over n. So we defined it that way. So for us to make sense of the definite integral and the definition, we need to define what our symbols mean. And delta x is going to mean b minus a over n, and that's the width of one particular rectangle. And notice we've made all of those widths the same. So we don't have a different delta x for each rectangle, but one delta x for all of them. They're all the same. So that's dividing that b minus a up into equal little horizontal pieces of width delta x. And notice that as n approaches infinity, the b minus a is fixed in the top. That's just the width of our interval. But the n is going to get larger and larger in the denominator, which makes the whole fraction smaller and smaller, closer and closer to 0. So notice that the widths, delta x, approach 0 as n approaches infinity. That's going to be an important piece of this. Now, in the notation, what else do we see? Well, we basically set up the notation for a right Riemann sum. Let's look at that again. So we let delta x be b minus a over n, and x sub k is the x value at the right end of each interval, which we've seen before is a plus k delta x. So we take that x sub k, find the y value that goes with it, the f of x sub k, multiply it by a delta x. So the f of x sub k is a height, or a y value, which is a height of our rectangle. The delta x is a width of our rectangle, so that product is the area of one single rectangle. Then we want to add that up. So we use this Greek letter sigma standing for add 'em up. So think of this for standing for sum or add 'em up in the discrete case. Notice that we're adding a whole rectangular area in each time we get to it. So we're adding these in discrete chunks. And then we want to take the limit of that as n goes to infinity, and that's going to be our definite integral. So notice in our notation, look what happens. The delta x sort of gets replaced by dx. The f of x sub k is just f of x, because now we're not thinking of these as discrete jumps in x, but a continuous flow as x flows from left to right. The y's flow from this as f of x. And then, so then we sum that up. So now this s, a Greek sigma, is replaced by a long skinny s called an integral sign. And this is a stylized s for sum. So think of the sigma as the sum of a discrete number of things that come in chunks, whereas the long skinny s, the integral sign, is the sum in a continuous case. And notice this is going from sum a to b, which define this interval, so those a and b are given in the formula there for the what we call the definite integral. So in our class, this will be the definition of the definite integral. So the a is called a lower limit, and b is called the upper limit of the integral. The f of x is called the integrand, and then the whole thing is called a definite integral. Okay? One way also to think about this sums is like the difference in peanuts and peanut butter. You know, when you're doing a discrete sum, it's like peanuts. They come sort of one at a time. Okay? You get a whole peanut or not. Okay? Whereas over here with peanut butter, it more comes in a flow, in this kind of spread there. So just kind of an imprecise, but an analogy to help think about these two different kinds of sums. But in both cases, they're s for a sum. Now, I will need to say this just to be precise here. This definition we're using here, in a way, is a slight simplification of the more general definition you may find in some textbooks. In actuality, it's not necessary that we specify that the x sub k's had to come at the right end of each subinterval. In fact, they could be any x's in the interval. And then, so you don't have to use the left end or the right end or the midpoint. We could use somewhere, anywhere in the interval. Furthermore, you don't really even have to make all the delta x's the same width. You just have to make sure that as n approaches infinity, the widths of all of the subintervals approaches 0. So if we could state that precisely, that would be more the formal definition of the Riemann integral, the more general formal definition. So with that definition, we would say that if we have an interval from a to b, and a closed interval from a to b, and a function for which the Riemann integral is defined, that is, that defining limit exists, then we say that function is integrable over that interval. In more advanced classes, you can prove that if a function is piecewise continuous on this interval, with perhaps only a finite amount of jump discontinuity, so not vertical asymptotes, but little jumps, so like left and right limits are defined, but not necessarily full limits, so we have some discontinuities, then that function is integrable on that interval. So basically, for most of the functions we'll be dealing with, they will be integrable. And for our purposes, this definition I have above is slightly simpler, and it's going to be equivalent to the general definition for the kind of functions we want to study at least. So we're going to consider this the formal definition of definite integral. So let's go over the formal definition just one more time. We start by having, to make sense, we got to say everything that's in the box here. So to define the definite integral, we let delta x be b minus a over n, and x sub k be a plus k delta x. Then the integral from a to b of f of x dx is defined to be the limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k times delta x. So again, delta x is the width of an interval, f of x sub k is the height at the right end of the interval, the way we defined it here. So then we multiply that, we get an area of a single rectangle. We sum that up, we get a right Riemann sum, take the limit as n goes to infinity, and that gives us the definite integral.